Hello and welcome to today's IWCS webinar. Now I'm pleased to turn the webinar over to Ed Vinton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we are pleased to welcome Kirsten Langfeld, Material Scientist, Corning Optical Communications, Berlin, Germany, who will be presenting her paper on investigation of reliability of the test for assessing reaction to fire of cables according to the Construction Products Regulation. Kirsten Langfeld received her master's degree in chemistry in 2007 from the Technical University of Munich in Germany. In 2012, she completed her doctorate in technical chemistry at the Technical University of Berlin, Germany. During her postdoctoral studies at the Federal Institute for Materials Research and Testing, BAM, in Berlin, she mainly focused on flame retardant properties of polymers and burn performance testing. She joined Corning Optical Communications in 2014 as material scientist working in the materials group of the technology department. Kirsten, we welcome you to present at today's IWCS webinar series event. Please go ahead.
Thank you very much for the kind introduction, and thank you all very much for joining my presentation with the topic, as it was already announced, investigation of reliability of the test for assessing reaction to fire of cables according to CPR. The work was mainly done by Thomas Meyer and Kirsten Langfeld, so myself. We are employees of Corning Optical Communications, which is a manufacturer for fiber optic cables. This presentation was already held at the IWCS conference in October in Orlando, Florida, and today I will represent the same presentation without any changes in it. During my presentation, first I would like to give you a short introduction and a little background to the topic. Then I would like to talk about the repeatability of the EN50399 test. Afterwards, I would like to talk about the reproducibility of this test. In the main part of my talk, I will present results for the impact of the variation of test conditions on this test, and in the end, I will conclude. So let's start with the introduction. In 1969, 17 people died in Düsseldorf airport due to burning PVC cables. One of the steps taken was to introduce the Construction Product Regulation, or CPR, which is now obligatory since the 1st of July 2017. And it claims that all materials or products which are permanently installed in buildings must be tested and certified according to their behavior in fire. This behavior in fire, or the test results, are matched into classes ranging from A, high performance, up to an F, low performance. Fiber optic cables, a realistic range for those products is a B2 up to an F. And one of the tests which is mainly determining the class is this EN50399 test with a 20.5 kilowatt flame. This test delivers certain parameters, so the flame spread, the burnt length along the ladder in meter, some heat release, and some smoke release parameters. Here. Based on those parameters, the class is determined. Sorry. So let's have a look on the test. The test in the end is an oven 4 meters in height with the air supply inlet on the bottom and the gas outlet in the top of the chamber. Above the chamber is a hood not connected to the chamber. In the end of the exhaust pipe is an extraction fan. In the back of the chamber is a ladder with the cables mounted on it. In front is a burner with a 20.5 kilowatt flame. And in the end of the exhaust pipe is a gas sampling where the heat and the smoke release parameters are determined. So the first thing we were asking ourselves is, what is the repeatability of this test? Since we were looking on real cables tested in it and the results slightly varied, we thought it's a good idea to look on the repeatability with a kind of calibration cable. So we invented this calibration cable, which is shown here. This calibration cable has a very simple design with low complexity. It has a GRP in the middle, followed by a polyethylene layer, so a material which combusts very fast with a rather high peak of the heat release, followed by an FRNC material, so material which is combusting slowly with a rather low heat release or peak in the heat release. And due to this mixture of these different materials, we wanted to achieve an intermediate burn performance. So we wanted to have a cable which is not burning to the top of the ladder, but we also do not want to have a cable which is not burning at all. In addition, this calibration cable had an outer diameter of 10 millimeters, so a rather large diameter in order to reduce the mounting effort. So as you see here, these are only 15 cables which are mounted per ladder, so the ladder is prepared pretty fast. And as I said, the main purpose of this calibration cable was to reduce the intrinsic variations originating from the cable itself. With this cable, we wanted to test the repeatability. So what we did is we burned this cable 100 times over a period of 20 months, always with the same conditions as defined by the standards. And what you can see here is now the mean out of those 100 experiments for each of the parameters. And the first thing we see is that our calibration cable really is burning, or the flame spread of the calibration cable is somewhere halfway up the ladder. So this is exactly what we were aiming for. And what we also see is that added below the means are the sigma values of our parameters. And those sigma values are for 100 experiments rather low, and they match perfectly with the safety margins, which were defined in prior projects, so by CMAC 2 project. And those sigma values and safety margins are in a good match with each other. So this calibration cable is suitable to monitor test results. It's also suitable to monitor your repeatability, or if, for example, if your equipment is still performing in the same way as it was doing last year, for example. Another point where we were thinking about is that this calibration cable is also a very good and capable tool of testing and monitoring the reproducibility throughout different laboratories. And this is exactly what we did and what I would like to show you now. So what you see here is a Gaussian distribution based on those 100 experiments I showed you before. And added as lines are the results of laboratory 2 to 5. And what we found is that laboratory 1, 2, 3, they are all right within this normal distribution of this flame spread. But laboratory 4 and 5, they are out of this normal distribution. If we want to have now a more detailed look on the results, what you see here, and let us focus on the flame spread, then we see that laboratory 4 and 5 have only half of the flame spread what was achieved at as in laboratory 1 and 2. At this point, I of course have to add that in Laboratory 1 we had 100 experiments, and Laboratory 2 to 5 only 1 to 3. So there is not such a statistical confidence behind these values. However, during our 100 experiments, we never achieved flame spreads below 1 meter. So this is was a very unusual situation or result for us, especially because CPR classes do scatter here from a D up to a B2. So the strong question came up for us, what is causing those deviations? And we thought about, or we did a big test plan in order to assess the impact of different variations of test conditions on the flame spread. And this is exactly what I would like to show you now. So we did a big test plan with our calibration cable. And the first thing was we were studying the standard in order to identify parameters which are not stringently defined or not defined at all or defined in ranges. In general, one can separate those parameters into parameters dealing with ventilation, dealing with sample preparation, or dealing with the equipment. So in sum, we performed more than 200 experiments covering all those identified variations within the standard. And due to brevity, I cannot show you all of those experiments. So today, I would like to focus on the mounting procedure for the sample preparation, for the condition of inlet airflow for ventilation, more precisely on the humidity. And for the equipment, I would like to present you the results for chamber build differences. So let's start with the mounting procedure. The first, or mounting, let's say it like that. Mounting in the standard is defined in regards of the distance between the cables, that one cable outer diameter distance needs to be between those cables, and the overall width should be 300 millimeter. We were wondering what happens if the distances are a little bit smaller, somewhat like 8 instead of 10 millimeter for our calibration cable. Yes, the overall width would be reduced, so you could measure that it's smaller. But let's say if you're just having a look on the ladder, as you see it here, you cannot identify that it's really a smaller width. However, if you have a look on the results, you see that the flame spread was lowered by approximately 50 centimeter. I'm saying approximately because each test was repeated 1 to 3 times, and it's always an average out of those results gained. The next thing was to look on alternating distances. So what that means, okay, if the overall width stays 300 millimeter as defined in the standard, but the distances are not measured accurately enough. So we have 7 and 13 and 8 and 12, something like that, millimeter distances. And what you see is that we found that the flame spread was lowered by approximately 30 centimeter just by applying alternating distances. And here we really want to highlight that it is important to ensure the correct distances during the mounting, because this can lead to variation. The next thing is the cable tension along the ladder. So we did this test not with the calibration cable, because the calibration cable is too stiff to apply different tensions. And we took a cable where we applied a low and a high tension along the ladder. And what we found is that if we apply a high tension, the flame spread is lowered by approximately 60 centimeter. And this tension along the ladder is not defined in the standard. The next thing about mounting is the wire fixation strength. So the standard defines that the cable is fixed on the ladder with 2 wires mounted crosswise around the rung and the cable. But the strength with which the wire is fixed is not defined in the standard. So we took again a more softer cable. The calibration cable is here too stiff to really mount it in a different way. But with the softer cable, as you see here, we applied a loose and a more tight fixation. You also see that these are not really extremes. These is still within a normal variation range. However, if we are looking on the flame spreads, we see that the loose fixation delivers a flame spread which is lowered by approximately 60 centimeters compared to the tight fixation. But the fixation strength of the wire is again not defined in the standard. Let's have a look on the bundle density. If we vary the bundle density, if we increase the density by tension, for example, or by adding an additional metal wire around this bundle, we can increase this bundle density. And what we found is that with an increased bundle density, the flame spread is decreased by approximately 50 centimeters. But also, again, the bundle density is not defined in the standard. So here at this point, one really has to mention that for mounting, there are some parameters, some conditions still not good enough defined, which leaves room for variations. The next is the ventilation, so the humidity of the air supply. Let's have a small dive into theory. If we are looking on the left side on two containers with the same volume of air. So one is with no humidity, the other one is with 100% humidity. Then we see that for the 100% humidity, we have less oxygen and nitrogen being present in the same volume of air, so less oxygen being present for the combustion. And in addition, we have water molecules being present, which might lead to cooling effects during combustion. So we were looking into literature and trying to find some evidence for this, and we found some studies dealing with that. So this study here on top, this group was dealing with the flame spread through randomly packed fuel particles. And what I want you to focus are the red arrows now. So if you see here the flame spread rate for here for measured with a 95% relative humidity of the air supply, and here measured with 24% relative humidity in the air supply, you see that the flame spread rate is increasing with decreasing relative humidity of the air supply. The same trend was found by this group, who were studying the flame spread over filter paper. They found also that the flame spread is increasing with decreasing humidity of the air supply, and they were looking on the mechanism behind. And on the one hand, of course, they found that filter paper is absorbing water, but more interesting for us, they found that the heat transfer from the flame is changed with increasing absolute humidity. As you see here, the heat transfer from the flame is decreasing with increasing absolute humidity. So this is exactly, that's what we were supposing, and so we had a more detailed look on our experiments. So these are now our experiments. You see, we put the trend line inside, even though they do scatter, you see this, but we put this trend line inside, and you see that for the left end, we have something like 2 grams per cubic meter absolute humidity, so that would be something like 12 degrees C and 20% relative humidity. And the right end of this trend, we have something like 12 grams per cubic meter, which would be something like 26 degrees C and 50% relative humidity. And the flame spread between these 2 points, the difference is approximately 25 centimeters. That's what we found for our experiments. Since you heard, we are sitting in Berlin, and we are a little bit limited in the absolute humidity of air, of our air here, and also the technical realization was not so easy for 8,000 liter per minute. So we could not test the rest now in practice. We extrapolated this trend now to really high absolute humidities. You see, I highlighted the point for 41 grams per cubic meter. This is a really high extreme. In October in Orlando, where this IWCS conference was, we had something like 30 grams per cubic meter, and that was for me already an extreme. However, this 41 gram per cubic meter, they would be still allowed by the standard because this would account to something like 40 degrees C and 80% relative humidity. That would be within the standard. But the extrapolation shows that here we would have a flame spread which would be below 1 meter 30. So this would be a B2 rating for our C cable just because of the humidity. And again, the standard is not defining anything about the humidity. So last point, the equipment, or more in detail, the chamber build differences. If I'm talking about the chamber build differences, I'm actually talking about the air distribution in the chamber. So what we did is we did CFD, computational fluid dynamics simulations of our air distribution. And that's what you see here. You are looking now on the side of our chamber. Here's the door. Here's the back wall with the ladder. Here's the air inlet, and here's the gas outlet on the top. And we are looking now on a low velocity regime. And what we see is that this is a very complex air distribution situation with several turbulences occurring. If we are looking on the high velocity regime here, then you see that here are not so much turbulences, but you see that the main gas stream now is here on the in the back of the chamber, being distributed around our ladder. Some before, in front of the ladder, at the cable surface, a little bit behind. So this is how it looks in a normal situation. Let's say like that. So what we then were simulating was, what if we are adjusting to our chamber some kind of ladder positioning tool? Because the standard is not defining how to fix the ladder in the chamber and how to position this ladder in the chamber in the correct position. So what one might think about is just a baffle in the back here as contact point for this ladder to ensure always the correct position. So we simulated this kind of baffle, and what we found is that now the main gas stream in this high velocity regime is on the one hand shifted to the back wall away from the cable surface, and on the other hand the velocities are increased. So heat and gas are removed faster from the chamber and more away from the cable surface. So, of course, we were wondering how this impacts the flame spread. So we tested this. We installed this kind of baffles in our chamber. And what you see here is now an average number. That means that this is, we tried out many different designs of baffles. And one has really to say, strongly dependent on the design of this baffle, the flame spread changes. This is now just an average number to give you an idea that baffles or additional installations, they do not only change air distribution, they really change also the flame spread. Again, how much they change it, that depends on the design and the solution, what is implied into this chamber. The next point, how to, let's say, change air distribution in a chamber is the sealing or leakages. So again, a CFD simulation of our chamber, but now you are standing in the door, looking on front of the burner into the chamber. So this is the burner, and this is the gas or air distribution in this chamber upwards in a high velocity regime. For a sealed burn chamber, and what you see is that this is very homogeneous, very symmetric, and there's not so much happening around this gas stream. So now I would like you to focus on this, on the center part here, on this white area. If we are now adding some leakages to our CFD simulation, what you see is that now the gas stream is shifted to one side. It's asymmetric, and there are way more things happening here around. The next very important thing to look at is, of course, the temperature distribution of the flame then. So air distribution and gas distribution is changing, so probably the temperature distribution is changing as well. So we were simulating this as well and looking on it. Here you see again the sealed burn chamber, and what you see is that here the temperature distribution is very symmetric and very homogeneous. But now I would like you to focus again on the red part here. If we are now adding some leakages to our chamber, do you see that the temperature distribution is now shifted again to one side, like you saw it before for the air distribution? So the flame or the temperature distribution in the flame is now asymmetric, shifted to one side. So that means that our temperature is also, or the temperature distribution in the flame is also very sensitive towards changes of the sealing of our burn chamber. So we were interested, can we prove that in practice? So what you see here is now the burn chamber as it is here in Berlin. And we closed this burn chamber, but we left here a small gap of 10 millimeters in the door. And then we tested again our calibration cable, just under normal conditions. And what we found is the following. We found that now the flame spreads are the half of that what we got before, just based on this gap here. And what we also saw is this asymmetric combustion pattern. And this asymmetric combustion pattern was is in pretty good match with that what we simulated from the temperature distribution of the flame. So this asymmetric combustion pattern seems to be a very good indicator that this air distribution is changed in this chamber. So as I said, we performed in some more than 200 burn experiments, varying all parameters which we identified, which are not stringently defined in the standard. And we found for the calibration cable that the flame spread is impacted by the mounting procedure, that's what I showed you, by the condition of air inlet, humidity I showed you, by the cleanliness of the burner phase, I did not show you, but that means that if soot or polymer melt is blocking the burner phase, one might get again an asymmetric temperature distribution of the flame, which again impacts the flame spread. So we do recommend to improve the standard in order to define certain parameters more stringently. The last point I showed you were chamber build differences, or better, a changed air distribution in the chamber and how sensitive the flame spread is towards this air distribution. So we really recommend here that one should look for a way how to ensure a reproducible air distribution in these burn chambers. So my conclusions in the end, I showed you the calibration cable, and we recommend to introduce a kind of regular test with such kind of calibration cable throughout all laboratories in order to improve and monitor the reproducibility. I showed you that the deviations which were observed, we could explain them by the variation of parameters which are not stringently defined, enough defined in the standard. And we recommend to adjust the standard in order to reduce those variances. At this point, I want to add that since October, when this presentation was held at IWCS, Corning continued its work on this topic, and also Corning continued to participate actively in different committees. And there is more work going on, and also starting from committees, there are more activities started and planned for the future in order to make the standard better, something like round-robin tests and so on. Things were started, and yeah, this is one outcome, and I really wanted to highlight here for you. In the end, I would like to thank certain people for supporting this work, and I would like to thank you for your attention.
Thank you, Kirsten. At this time, we will ask as many questions from the attendees as time permits. I'm going to start with the first question I believe you started to answer at the end, but the first question is, since the presentation of this paper at IWCS, what has happened in Europe?
So as I said, that there are Corning continued and also increased the work in committees and the activities, and I know that round-robin tests and were started, and Corning continued a lot of research on the topic. But to answer that question in absolutely depth, I would really refer to this question after the meeting in order, because now I cannot dive into all activities which were started. I know that there were a lot of like round-robin tests, but I do not have a more detailed answer now here.
Okay, thank you. Next question. Do you think lab-to-lab variations could be due to the location or altitude or local barometric pressure?
Yeah, this is a very interesting question. I was actually analyzing the data in regards of all this, and of course, if we are talking about absolute humidity, we are talking also something like dew point and barometric pressure and so on. But honestly, it is not really the location and weather conditions itself that would be too easy to say. This is so barometric pressure, for example, it plays always into this humidity. Yes, they all belong together, all these parameters, but the analysis really showed that it is the humidity as main factor which is impacting the flame spread. And yeah, Germany has not such high humidities, but I think in Europe in general, the humidities are never like in the jungle.
Okay, thank you. Next question. Is reproducibility of cable fire testing better or worse with bundled cables versus cables with spaces between them?
This is a difficult question, and to be honest, to answer this question, I really would need to have a more deep dive into the results in order to give a good explanation to that. So I would be happy to answer this question with the team after the webinar.
Okay, thank you. Next question. With the impact of ambient temperature, humidity, and airflow on the test results, are labs required to provide consistent or controlled room conditions for the test chamber during the test?
That's an interesting question. So that would be one solution I could think of, but actually, to be honest, to decide that, I'm not in the right position, and there are still data missing to really prove that. But from that, what we know, what we learned from the study, that would help, yes, in order to make things more consistent.
Okay, thank you. Next question. The cable industry is spending large sums of money on a test that has a very poor documented test method. How did the EU approve and implement such a test, and when will these issues with the test standard be corrected?
So Corning don't want to make the statement that this is a bad test or that it is poorly documented. Actually, it's pretty well documented, but it's in the nature of burn tests itself that there are variations. So there are other material burn tests that it took like 30 years to make these tests really absolutely stable. I would really say this is not a poorly documented test. This is not what this presentation should give as takeaway message. It's a good test. It just needs more work and more experience. Sorry.
Okay. Thank you. Next question. How do you suggest that uniform tightness of wire ties could be implemented?
This is a very technical, detailed question. So, to be honest, there's now the word missing in English, but there are tools because the wire has loops in the end, and you could easily just apply measurement devices which monitor the pulling force. And for example, a pulling force would be one physical parameter which can be measured and documented. And yeah.
Okay, thank you. Next question: Which are the Senelec committees that are involved in CPR?
This is a question I really would forward to my colleagues. I cannot answer this now here at this point. It's something I would like to answer after the webinar.
Okay, thank you. Next question. If you optimized the fire test to cover all the variables you found, what is the comparison between your original 100 tests and these new tests?
To be honest, this is something we haven't done because that was not the purpose of the work. The purpose of the work was not to, I understand this question in a way that we adjust every parameter in the way that we get a low flame spread. So this is not the purpose of the work, and we've never done such a comparison.
Okay, thank you. Next. Is there a need to retest the cables already validated with the new advised, more defined conditions? What about the current cables' classment reliability in the market?
This is a very interesting question, but I think I'm the wrong person to answer that. I mean, I'm more a scientist working on that. This is more a strategic question, and I can forward that to my team later on and to the right persons within Corning and ask for their opinion, but I cannot answer that. I'm sorry.
Okay, thank you. Next question. How do you compare the EN50399 to the tray cable test FT4 based on UL 1685?
This is, again, a tough question for me to answer because I do not know the standard now. Sitting here, I really don't know this now. I would need to read it and compare it. I'm sorry. I can try to answer that after the webinar, but not now here.
Okay, thank you. Next question is what do you recommend on outer jacket material, the constituent and its property? Is there any impact of volume of jacket material and cable size on the EN requirement?
This is, of course, an interesting question, but I would not answer it here in this webinar. And but what I can say is that, of course, also the results of these tests, they are dependent on the cable type. That's why I highlighted we tested it with our calibration cable. Of course, a different cable type might show a different behavior in our study. But for this question, I have no answer here.
Sure.
Sorry.
Okay, no worries. Next is what is your recommendation for cable tension while still maintaining loose ties?
Could you please repeat it once more?
Sure. What is your recommendation for cable tension while still maintaining loose ties?
Yeah, good. This is yeah. This is of course difficult to have loose ties and a high tension. And but the purpose of the presentation or of the work is not to trim the test in some direction. The purpose is to make a more consistent standard and to make test results more consistent. And and I think with this background, this question plays no role anymore, in my point of view.
Okay. Next one. Did Corning receive comments and questions from the notified bodies after the presentation at IWCS in 2017?
Since I am not so much part anymore of this kind of work, this is something I would love to answer after the webinar and to answer together with the team after the webinar.
Okay. Thank you. Next question. Do you believe that that the differences that the differences between excuse me. Okay, excuse me. The next question is, did you test the droplets and smoke release effect on these 200-degree experiments?
Yes, but that was not part here of this study, and this is too complex to answer this now here and within this webinar. So this is also a question I would love to come back after the webinar with more detailed information instead of just a short question answer. Sorry.
Okay, very good. Thank you. Next question. Is the EN requirement applicable for outdoor cable? What F class is significant?
As far as I know, is this CPR construction product regulation only for indoor materials and products, so no outdoor application, and so my answer is no, I think.
Okay. And next question. Do you think modeling this EN 50399 test is really possible with reliability, or there is no sense to do that because nothing will ever replace a fire test on a cable?
This is a tough question, a good question. So the CFD simulation we showed are, of course, steady state simulations. And, of course, is a fire test way more complex. And as far as I know, there are activities on modeling this test. But, yes, it's a very, very complex test, and I'm not so deep into these activities of modeling that I can answer how far they are. But there are activities who really want to model this test. But my opinion, it's very complex. It's a tough piece of work, and but more I cannot tell you, unfortunately.
Okay, thank you. Thank you for that response. At this time, thank you, Kirsten, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Kirsten after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, April 20th at 10:30 a.m. Eastern US time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 66 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 14th through Wednesday, October 17th, 2018, at the Rhode Island Convention Center in Providence, Rhode Island, USA. In addition, the second annual regional UL and IWCS China 2018 Cable and Connectivity Symposium will take place next week on Tuesday, March 20th through Thursday, March 22nd, 2018 at the Shanghai International Convention Center in Pudong, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.